Hello everyone, welcome to the video lecture of this course finite element method. So this is the last lecture of the sixth module that is known as computer implementation or the software simulation actually. So in the earlier lecture we have studied and we have discussed in details the basic three steps of this finite element analysis, and there we have seen that total 10 steps are there under these basic three steps. So the three basic steps like the pre-processing, then analysis or solver, and the post-processing, these three different steps we have discussed in details in the last lecture. Then we have discussed in details the concept of the discretization, then the numbering of nodes, then the implementation of the boundary condition. After that, the material properties, then the calculation of the stiffness matrix, then the post-processing part where we will calculate the result. So all these different steps we have discussed earlier in details. So today we will discuss some more details of the software simulation part, and one example we will discuss based on the non-structural finite element method, which is basically the thermal problem. So what we have seen that in case of the structural problem we find the displacement, then stress, strain, all these things. But in case of non-structural problem, which basically deals with the thermal and fluid part, so there we will basically find the heat transfer, then fluid flow properties like velocity, pressure, temperature, all these things we actually find there in case of the non-structural problem. So today we will discuss one example of this non-structural problem and the software simulation tool actually, what the software actually does in case of this finite element method. So all these things will be discussed in details in this lecture. Okay? So let us start this lecture. So first we will discuss the finite element analysis software. Now in the field of this engineering analysis, the finite element analysis programs, they occupy actually a major computational activity. A large number of general purpose program packages are developed for stress analysis of complex shape and material properties and boundary condition in various areas of the engineering design, such that the machine components, then the pressure vessel, boiler, nuclear, offshore structure, all these things. So these are some application area in case of the engineering design where the finite element analysis software is widely used. Now what happens in case of the structural analysis program? This finite element analysis program for static and dynamic analysis of linear structural system. The program is coded in standard Fortran for operation on CDC 6400, or you can say 6600 or 7600, such type of computers. Again, SAP4 is a non-proprietary medium-sized package, and so it is widely used in academic and some practical applications. What is this SAP4 actually? This program, SAP program, has 9 element types, and the structural systems to be analyzed may be composed of combination of these elements in case of this SAP. Now the capacity of the program, it actually depends on the total number of nodal points of the system. then the number of eigenvalues which are needed in the dynamic analysis, and the main memory allocation of the master array. Now, the concept of the node or nodal points, then the concept of the elements, these are already discussed in the earlier lectures. Now the static analysis, it is continued by solving the equations of equilibrium, which is followed by the computation of the stresses. But in case of the dynamic analysis, there are various options available, like the frequency calculation only, then frequency calculation which is followed by response history analysis, then there is frequency calculations which are followed by response spectrum analysis, and the response history analysis by direct integration. So these are the various options available for the dynamic analysis in case of these finite element analysis problems. So this is the basic concept of the structural analysis program. Now there are various finite element analysis software packages. So what happens actually, the rapid advances which is made in computer hardware and software, it led to the significant development in case of the finite element analysis software. This finite element technology, including foundations of mechanics and numerical analysis on the one hand, and the computational skills in areas of software technology, including the program techniques, then the data structure, database management, and some computer graphics, these are there. So there is a rapid advancement in case of this finite element methodology, which is seen in the recent past. And in case of this finite element analysis, for different types of problems like static, then dynamic, then material and geometric, linear or non-linear, then the coupled situation, then in case of the non-structural you are having the heat transfer, fluid flow, and for all these things the pre and post processing features we need to apply all these basic 3 steps which we have discussed earlier. All these things we need to apply for different types of problems that will be solved using this simulation tool. And there are actually various finite element packages like Abacus, then Adina, then ANSYS, SAP, then Cosmos. So all these are various software packages through which we can solve these finite element analysis problems. So in our computational laboratory, we are having this ANSYS software, and through this software or the simulation tool, we will practice various problems for this finite element analysis. So there, for structural and non-structural problem, we will try to solve various physical problems, and through this ANSYS software we will see how to proceed step by step to get the final result. So several software packages I have said just now, like Abacus, ANSYS, SAP, then Adina, Cosmos. So there are several major features for all the software, like they are having some element library, then there is analysis capabilities and range of application for each and every software, and types of loading are there, then boundary conditions and models, these are there, and material properties that we need to define in the pre and post processing, then interfaces with CAD or CAM system, and finally the design optimization. So these are some major features of all the software packages. So let us move to the next slide. So today I will discuss one non-structural example for this simulation tool. So this figure 1 here, the concept of working of the ANSYS simulation tool, it is shown by schematic diagram. So in the first diagram we can see there is a black box given and some user inputs are provided at the left side of this black box, and in the right side of this black box some color pictures and other results, these are shown. So what is this actually? The simulation tool in case of this ANSYS, it can be considered as a black box. So what happens in this black box, some user inputs, these are provided and some working or some operation going on or goes on inside this black box, and finally some color pictures and some other results are achieved. But what happens inside this black box? So we need to know the basic operation which occurs inside this black box. So in our case actually this ANSYS, it is the black box, the software simulation tool that we will use. This ANSYS, it is the black box and it actually applies to any comparable simulation tool like Abacus, Edina, SAP. So this concept applies to any comparable simulation tool. On the second diagram here you can see that one physical problem, one box is given where it is written physical problem. So what happens that suppose one physical problem or a real life problem is given to us, so that we can solve by the software simulation to get the optimized result. So in that case, based on the user inputs related to the physical problem, the software will solve the mathematical model which is based on the physical problem. So that means the tool or the simulation tool, it does not solve the physical problem. Rather, it actually solves a mathematical model which is based on this physical problem. Suppose in user inputs, we need to first draw the geometry of that model. Then we need to perform the meshing, which is actually the discretization. So the concept of this meshing or discretization is already discussed earlier. So we have seen that the discretization means we need to subdivide the total structure into several number of finite elements, and ultimately the numerical solution is done for each and every element, and finally the result is assembled. So after the geometry modeling, we need to perform the meshing or the discretization. Then in the user input, we need to provide some boundary conditions and some material properties. So these are some user inputs that we need to provide in this black box. And all these inputs, these are based on this physical problem. And there are some physical principles or assumptions like equilibrium, then conservation, and these assumptions, these are actually embedded within the mathematical model. Now based on these user inputs and the physical principles or assumptions, the simulation tool, it will solve the mathematical model. So here you can see one numerical solution, it is written. Then the simulation tool, it will solve the problem numerically, and after that at some selected variables and at some selected points the results will be achieved. It means this simulation tool will not calculate all the variables directly. It will actually calculate selected variables at selected points, and at the post-processing part some color pictures and some other results, it may be in graphical form, or color pictures means some contour plots. So these are the things that we will find or we will achieve at the post-processing part. Now inside this black box, these are the things happen, that is the simulation tool, it does all this, it performs all the steps. Now how to validate our result? So you can see in the physical problem, two arrow signs are given and it is written hand calculations and experimental data. So based on the various user inputs, we can either perform some hand calculation, that is some analytical method to find the result, and with that result we can compare the result obtained through the simulation tool. We can do another thing, that if the experimental data is achieved for that physical problem, then we can also compare the result achieved through the simulation tool with the experimental data, which is the real life data actually. So in these two different way we can validate the result obtained through this ANSYS simulation tool. Like in case of the solid mechanics simulation, we will calculate the displacement, then stress, strain, all these things, but in case of the fluid mechanics simulation, we will calculate the pressure, velocity, lift, drag, all these things. So this is the working principle or the concept of working of this ANSYS simulation tool that I have discussed just now. Next, let us take one example. So from some established or some published paper in some renowned journal, I have taken this example. So this some simulation steps now I will discuss for a non-structural problem. So this problem is basically related to the wind energy. So it is related to the fluid flow. The air is the fluid here. So actually some performance improvement of wind turbine has been done in those software, in those papers that I have considered here. So all of you know that in case of any wind turbine, it may be horizontal axis or vertical axis, the blades rotate. They actually convert the kinetic energy of air into mechanical energy, and finally this mechanical energy is used to generate electricity. So this is the working principle of the wind turbine. Now to improve the performance or the power coefficient of this wind turbine, there is an important parameter, that is the blade shape or blade camber, and improving which or modifying which we can improve the performance or the power coefficient of wind turbine. Now, here three different wind turbine blades have been chosen by going through the literature study. That means the authors have studied a number of papers in this field, and from that they have identified some research gap, and finally some objectives have been chosen. So these are the three different blades which are selected based on their experimental result, where it is seen that they are popularly used in case of the wind turbine, so that standard or significant amount of power coefficient is achieved. Now three different blades are chosen here. Number one is NACA 0018 blade profile. The number B is S815 blade profile, and number C is EN0005 blade profile. And here you can see some fabricated blade profiles. The schematic diagrams, that is the outlines, and the fabricated blade profiles, these are shown here. Now here the vertical axis wind turbine it is chosen, and in case of this vertical axis wind turbine, the axis of this turbine, this is actually perpendicular to the ground level, and these vertical axis wind turbines are having several advantages over horizontal axis wind turbine. So I will not go into details with this theory part of the wind turbine. I will just discuss the steps that is performed with in this ANSYS software. So first we have done the geometrical modeling. So here you can see that figure 3a, 3b and 3c, using these three different blades, that is S815, EN0005 and NACA 0018, we have drawn the vertical axis wind turbines. Now the blade dimension, these are chosen from from the literature study actually. So here you can see the 3D view as well as the two-dimensional view, that is the top view of this vertical axis wind turbine, which is also known as the H rotor or H Darius rotor actually. And this 3D view, these are drawn for better visualization or better understanding, and in the paper the simulation is actually done on the 2D view that you can see in this top view shape. Next, we need to draw one computational domain, and that computational domain it is also shown in 2D and 3D view for better understanding actually. So this computational measurement of the computational domain, it is taken from the literature study from some standard published paper. So here you can see one computational domain, it is there, and in the left side of this computational domain, the free stream velocity, it is the velocity inlet, and then the right side of this computational domain we are having the pressure outlet. In the top and bottom side of this computational domain, these are considered as symmetry or the wall. Now the turbine circle, here at the top view of the turbine, that we can see it is the inside this circle we are having the rotating inner domain, but outside of this circle we are having the stationary outer domain. So all these things can be seen in this 3D view also for better understanding. The velocity inlet, then pressure outlet, and the symmetry, that is the side walls, they should be sufficient distance away from the turbine boundary. to get the approximate or the accurate result. So after the geometrical modeling part, we need to perform the meshing or the discretization. So we know that it is in this step we need to subdivide the total domain into several small finite elements. So here you can see that the meshing it is done, and the triangular shape of elements we can see in the leading edge mesh. Okay, so we have zoomed in that leading edge mesh where you can see the triangular shaped mesh. This has been considered, and in the blade periphery we can see that the mesh is much denser compared to the other regions. So the logic is that the air pressure and air velocity, these are actually there is a sudden change of this air pressure and air velocity at the surface of these blades and near to the wind turbine. So to acquire or to grasp the sudden change of velocity and the pressure near to the blade surface, the mesh should be denser. Otherwise, we will not be able to capture the exact result. Now, in this figure 5b, we can see one grid independence test. So, this grid independence test is very much necessary to get the accurate result. And here the grid independence test is done with respect to the pitching moment coefficient. So the higher number of elements they lead to the result which is approximate but within acceptable limit, and which is very much closer to the real life result. So this grid independence test, it is very much important in this finite element analysis. Next, we need to put some boundary condition, that is the air velocity at the inlet, then the outlet pressure. So all these things we need, all these boundary conditions we need to provide. Then the material properties, then air density. These are some more boundary conditions that we need to provide. After that, we need to choose the suitable turbulence modeling for this non-structural problem, because all these problems, these are basically turbulent in nature. These real life problems, these are basically turbulent in nature, and so some turbulence model, some suitable turbulence model need to be chosen. So in the software there is the option to choose the suitable turbulence model. There we will see various turbulence model which are known as K epsilon, then K omega, where K is the turbulent kinetic energy, epsilon is turbulent dissipation rate, omega is specific dissipation rate, then SST K omega, which is shear stress transport K omega model. So various such turbulence models are there, and we need to choose wisely which turbulence model is suitable for our analysis. After choosing the turbulence model, we can perform the simulation in two different way, that is, one is for steady state and another is for unsteady or the transient state. And after that we need to provide the iteration steps. In the software we will perform the number of iterations, and when the iteration will get converged, then we will get some contour plot of the static pressure or velocity magnitude. So here we have reproduced those contour of static pressure when blade positions are 0 degree, 120 degree and 240 degree for these three different blade edge rotors at 6 meter per second wind velocity. So from this contour plot, we can see in the legend various pressure magnitude these are written, and corresponding to the color combination inside the turbine circle, corresponding to the color combination, we will identify that the pressure magnitude at that point this is this much. So this contour plot, it is very much necessary. Next, this is the wind flow streamlines when blade positions are theta is 30 degree and 270 degree. So some question mark it is showing here, these are actually theta it was written, so maybe due to some technical error it is not showing. So this theta you can see in this diagram. So these are some wind flow streamlines. These are plotted when the different blade profiles of this S815 and EN0005 and NACA 0018, these are actually plotted for theta equals to, theta is the azimuthal angle actually, so for this theta equals to 30 degree and 270 degree, this blade wind flow streamlines, these are plotted, and we can see here that for theta equals to 30 degree, in case of the first and second diagram, that is for the S815 and EN0005, there is a boundary layer separation at the suction side and some vortex or vortices are generated. So that means in those cases the lift generation will be lesser. And again in the returning stroke we can see that for theta equals to 270 degree, in case of the first and third diagram, that is for S815 and for NACA 0018, there is the boundary layer separation in case of in the suction side of these two different blade profiles, and the vortices these are generated here and these are revolving in nature. So based on this boundary layer separation and the formation of vortices, we need to analyze the reason, so, so that the whether the blades are capable of generating enough lift coefficient or not. And finally we will be able to draw similar kind of diagram, similar kind of graph actually, so where we can draw the lift coefficient versus angle of attack and power coefficient versus tip speed ratio, and we can also compare with the earlier published papers in this field to validate our result. So some experimental data and some CFD simulation data is also chosen here to compare and to validate the result here for the lift coefficient and power coefficient of these three different turbine blades. So this is the procedure and this which we need to follow to solve either structural or non-structural problems in case of if ANSYS simulation tool. Okay, so the basic three steps we need to remember always, that is the pre-processing, then analysis of solver, and the post-processing part. Okay. So we need to actually practice a lot of tutorial in this ANSYS simulation tool so that we will be comfortably perform any physical problem through the software simulation tool and we can get some accurate result. Okay, so these are the steps that we follow while performing the software simulation in case of the ANSYS simulation tool. Okay, so this is the end for this lecture.